Hi, everyone, and welcome to this Akamas Ignite webinar. Today, we will talk about Kubernetes-based applications, some of the insidious configuration issues that are unique to Kubernetes, and how full-stack application-aware optimization can help you and your teams be better running Kubernetes apps. My name is Matteo Fabiano. I am the CMO at Moviri and the head of marketing at Akamas. And I'm very, very pleased to share this virtual stage with Stefano Doni, a good friend and the CTO at Akamas. He is also a co-founder of Akamas itself, I should say. So hi, Stefano.
Hi, Matteo. Hi, everybody. Thanks for joining us today.
So Stefano has been around the block a couple of times, and he is what you would call a performance engineering geek, having spent the best part of his career first at Moviri and now at Akamas, working with all sorts of companies and organizations and innovating IT performance optimization itself and building capacity management solutions for these customers. Before I hand it over to Stefano, a quick housekeeping note. Today the webinar will be recorded and it is also a very fast webinar. It should take approximately 40 minutes, we hope. So be prepared because there's a lot of content to go over and it's going to be fast. We will have a couple of live polls along the way. You will see the poll on your screen and be able to answer in real time. And we hope we encourage you to do so. We will also hold a Q&A if we have time in the end, answering questions that are coming throughout the event. So you can use the GoToWebinar questions feature on your screen to ask questions to myself, but especially to Stefano. So with all that being said, I hand it over to you, Stefano.
Okay, thanks, Matteo, for the wonderful introduction. So welcome again, everybody, to the dark side of Kubernetes. It's great to see so many people interested in this topic. So hopefully we will have something interesting for you today. So basically today we are going to talk a little bit about some of the challenges that we have learned working with our customers, especially around how to best configure Kubernetes application to actually reduce costs, improve efficiency, performance, and reliability. And then we are going to see a quick demo about our product, how Akamas AI-based optimization can help you solve those issues and actually make your life better. So let's start with some usual statistics about operating system, while Kubernetes is becoming the default operating system for the cloud. So I'm sure that you all know about that, so not spending time on this one. Despite the fact that Kubernetes is being adopted by a lot of organizations, actually people are realizing that more and more, actually, it's becoming kind of challenging to manage application on Kubernetes. So first of all, the three main challenges that we want to highlight here is about cost efficiency. For sure, that's one of the most important ones. Actually, given also the current economic climate. So people, according to the FinOps report, actually are having a hard time to making sure that Kubernetes applications are as cost efficient as possible, so costs are increasing. But also there are aspects related to reliability and performance. So actually it's not that easy actually to run application in a reliable fashion or make the most out of the infrastructure, so making sure the application can deliver the best performance. So as you can see, there are many even high-profile companies that have talked about those kind of topics. So certainly it's not kind of easy to reach those kind of benefits that Kubernetes actually promise. And also there's this interesting side like Kubernetes failure stories where people are actually documented some of the most interesting failure scenarios that are around reliability, performance, and cost efficiency. So that's something very interesting to check out. So I guess the reason about that actually drives the main cause that drives some of those kind of issues is lies at the core of how Kubernetes actually manages the resources, which is around actually Kubernetes resource requests, being able to specify resource requests, resource limits for our containers. But it's not just about the way Kubernetes manage resources, but also it's very, very important to realize that what runs within the containers is actually playing a key role. Like, for example, most of the teams run Java application on Kubernetes. So how the JVM behaves, how the JVM is configured, play really a key role about actually being able to deliver efficient application, scalable application, and resilient application. So we are going to dive kind of deep into those kind of issues by highlighting actually what are the most critical challenges that we are seeing, we see working with our customers. But before actually jumping straight into the issues, we want to run a quick poll because actually we are always interested in understanding from you what is your most critical Kubernetes application management task today. So that's kind of interesting to hear what's your view on that. So Matteo, could you please run the poll?
Let's do that. Yeah, we're gonna give it a few seconds here for people to answer the poll. I see a third of you have been voted already. Please entertain us a little bit on this and answer the poll. Great. We're seeing some very interesting results. We're gonna close the poll in 5, 4, 3, 2, 1, 0.
All right.
Do we want to have a quick look at the results?
Yeah, sure. Why not?
So, Stefano, take it away.
Right. Yeah, that's very interesting. I guess that matches pretty right what we see in our customers. So I guess the most common answer is really about reducing costs. So as we said before, it's pretty common goal today, but also reducing manual optimization effort. It's actually some pretty common goals. So actually this kind of translate to people having a kind of hard time making sure that all your microservices are rightly tuned based on your goals. So that's very interesting results. So I guess we can now move to the actual facts. So we want to share with you today 3 facts, 3 main challenges that are somewhat counterintuitive about Kubernetes. So some fact that actually we see our customers are kind of making hard time to manage them, and they are related to about being able to deliver highly reliable, high cost efficient, highly performance application on Kubernetes. So let's start with the first one. So the first one again is about right sizing. So how can we actually reduce the cost of our application, like we had just said? So most of the times, Kubernetes actually allows you to specify the amount of resources that your container might consume. So let's take this example, which is basically a Java microservice running in a Kubernetes container, which is configured with 6 gig of memory limit. So in this example, which is based on real life experience, we are speaking about default JVM settings. So in this chart, you can actually see that the memory use is pretty low with respect to the memory limit. So it should be actually pretty safe to actually being able to downsize the memory limit of this application, actually save quite a bit of money. So is that kind of that easy? So let's see what happens if we actually decrease the memory limit of this container. So what you see in this chart is basically the result of several tuning experiments that we did with this particular customer, and actually that basically decreased the memory limit from 6 gig down to 2 gig in kind of incremental fashion. So in this chart, you can see the memory limit, again, memory use, container memory use again, but you can also see the response time of the application. So let's look at what happens to the response time of the application, and something very counterintuitive is happening here. So basically, as we reduce the memory limit, the response time of the application is going basically to the roof. You are having pretty kind of big impact on the performance of your customer. So the question really is, why is that happening? So it's something that we certainly are not expecting. So we are not certainly saturating the memory. So what is happening here? So the answer of this kind of fact, which is very interesting, is again related to what runs within the container. So in this case, it's a Java-based application. So it's a JVM that runs within the container. So basically, the JVM is basically auto-configuring itself. So the amount of heap memory is basically configured as by default as 20% of the memory limit. So starting from 6 gig, basically the JVM has 1.5 gig. And as you can see, as we go down with the memory limit, basically there's kind of automatic reaction by the JVM, which kinds of auto-configure itself with lower and lower memory. And what is happening is that at some point, actually, when the memory heap is about 1 gig or so, actually the JVM start to suffer memory pressure. So basically you have a lot of GC and a lot of performance impact. So that's kind of the real reason why actually several approaches, like when you need to resize your container, you don't need just to actually look at the memory usage. So basically it's not enough to look at metrics related to memory consumption over time, infrastructure metrics, but you also need to take care at what happens to the application runtime. Basically, it's not just about the JVM. Node.js behave the same. .NET is, again, very similar. So that's kind of important takeaway that we are sharing here. Let's now see the second fact. So that's kind of even more important for some teams. So being able to deliver highly reliable applications. So out of memory is certainly one of the most common reasons why application on Kubernetes actually simply get restarted without any apparent reason. So a lot of teams spend literally weeks in understanding what is happening. So again, we have a Java microservice here. So you now can see the memory limit. Now this time you can see the memory used basically goes higher and higher up to a point where basically it touches the memory limit. So the way Kubernetes works, in this case, basically your container gets killed, so without any prior notice. So that might translate to a availability impact, so a downtime on your application. So when people see this kind of actually evidence, so usual question is, okay, that's a misconfiguration or it's a memory leak. So usual answer is, let's come back to the development team. So there's certainly something strange happening on the application here. But let's just, in case, increase the memory. So that's the typical reaction. So let's increase the memory limits. Let's give more memory to this application in the hope that we won't get this problem anymore. So the real example, what is happening actually under the cover is that, again, it's related to the fact that how the runtimes works within the container. So in this case, the container had 1.3 gig, as you can see in the chart, and the JVM was configured with 800 meg. So pretty far from the limit. Nonetheless, you can see that memory usage actually is higher than the heap limit. So that's kind of, again, counterintuitive. So we find teams that actually cannot explain why the JVM is consuming much more memory with respect to the heap size. So it's something that it's typically not expected. So it's key to understand why this is happening, because actually, if you not understand the root cause, under this kind of condition, basically you are prone to have out-of-memory errors and actually availability problem for your application. So what is happening is basically actually pretty simple once you understand it. So basically the runtime, so what runs your application, again, that's the case for the JVM, is not only using memory for the heap size, basically heap where all your objects are going, but is also using memory with in order to actually allocate other data structure, internal data structure. It's called that off-heap memory. So off-heap memory, you need to account that also off-heap memory in your memory sizing for the containers. Otherwise, you're going to suffer those kind of issues. Problem is that off-heap memory is not easy controllable. So, and it's not that small. So we are seeing JVM with up to 1 gig of memory that is used just for the off-heap. So in addition to the heap. So basically, there are no settings, and the amount of heap memory usage really depends on the specific application. So here, the takeaway is really about understanding how your runtime manages memory. So again, we are doing a lot of examples for the JVM because actually it's one of the most common runtimes we see for being used by customers, but also other runtimes behave the same. So Node.js, the same. .NET, it's the same. So you need to understand how your runtimes allocate memory and make sure that you actually consider it in your memory footprint to better actually allocate memory limit and not suffer out of memories. So CPU throttling also impact, the third part is about CPU throttling. So the fact that it may impact application performance in surprising ways. So actually, if you read about the documentation about CPU throttling, actually, Kubernetes says that you should not have CPU throttling unless your CPU usage get really close to the memory limit, to the CPU limit. Actually, in this example, we see a lot of people that actually experience CPU throttling, even though the CPU usage is very low, so like 30%, 40%. So again, why is that happening? As related to go with about how Kubernetes manage actually CPU resources. So let's take a simple example. So let's say that we have a container where you have set CPU limit of 1 core. So basically, the way Kubernetes manages CPU limits is basically it considers periods of time, like for example, 100 milliseconds. Let's speak about the example on the left. And if you say, okay, I have one basically core available, this means that in 100 milliseconds, basically you get 100 milliseconds of CPU time. So you can run for one CPU 100 milliseconds. But let's see what is, and that is perfectly fine if your application has just one thread. But this is not actually how applications are built today. Applications today have many more threads. So if you consider the example on the right, so in the given period, like again, 100 milliseconds, if your application has, for example, 4 threads, they will actually burn up all the budgets, all the quota in a much less amount of time. Like after 55 milliseconds, basically, all your quota is gone. So for the rest of the period, basically your application will be throttled. So basically the app is stalled, so no business transaction could be processed in this period. So that is key. So that is kind of counterintuitive with respect to what we are used when we size, for example, virtual machine CPUs. And again, what is the key takeaway here? The fact that the runtimes plays a key role. For example, the way that you configure your application, how many threads, the thread pools actually is important, because you will have much more threads that will consume your CPU quotas, but even the runtime. So for example, on the JVM, again, if you select some specific garbage selector, serial will just use one thread. If you select G1, for example, more than one thread will be used in the background. So you get more chances to actually burn your CPU quotas. So the thing to realize is that with CPU throttling, there is no simple threshold that works out of the box for any application. So you may see from your tools, like observability tools, like I'm having 300 millicores of CPU throttling. But is that impacting for me? Am I slowing down my application? Or perhaps I can even lower my CPU limits without impacting the application performance. So I may even save money. So that's kind of the way CPU throttling can impact performance and cost in kind of subtle ways. So our key takeaway is that CPU throttling actually introduces a kind of performance and cost trade-off. So you need to experiment with, you can actually get a lot of performance benefits by tuning better your configuration, your runtime and your application before actually increasing the CPU throttling, the CPU limits and CPU requests, which actually typically translates to higher cost on the cloud, higher cost on the infrastructure. So that's one takeaway. Then the other thing is that you need to always monitor application performance. As we have seen, we may have CPU throttling that impact application performance, or some amount of CPU throttling may even be in a way acceptable. So we have seen up to 50% CPU throttling that is not translating into application performance issues. So that's kind of our experience as we are CPU throttling. So that is it. That of course translates. Let's zoom out a little bit. That of course translates to a whole lot of negative consequences about not being able to properly configure Kubernetes microservices. So as we have said before, on one side we have overspending. So our container may be basically too big, and that drives, of course, Kubernetes cluster resources and then cloud build. We may have bad user experience. We may even have availability problems. So that's kind of the issues, or as you said in the poll, actually, also a lot of teams are aware, of course, of those issues, but it takes really a lot of time. So a lot of manual effort to keep up with those configurations in order to make sure all microservices actually operate optimally. So that's kind of the impact. So hope that was interesting for you. Now, before moving to the actual solution, so how we can solve those problems with Akamas, we wanted to run a second poll, the last one, I promise, about how painful, based on what you have seen and based on what is your experience, is how painful is managing Kubernetes application for you.
Yeah, let's get the poll started. All right, let's wait a few seconds and see. I see your responses coming in. Our audience today is very fast.
Very fast.
In responding, too fast.
A lot of questions are coming through.
Highly optimized audience. Very good. So let's close the poll in 5, 4, 3, 2, 1. Thank you, everybody. So I'll share the results. Yep.
All right, so that's very interesting. I think that what we see is that the majority of the people is actually finding those kind of challenges extremely painful. So that is very interesting. Also painful, but survivable somewhat. So 26%. Some people actually are finding those kind of indifferent, or we can manage those. So that's also interesting to know that. So let's now see how we can actually solve those kind of problems in a much better ways. So basically, let me go back to the slide. So how we can solve those problems with Akamas. So basically, Akamas is an AI-driven optimization platform that we designed and we actually created based on our 20 years experience in doing this kind of optimization work for many enterprise, even prior to Kubernetes, of course. And now we are finding that most of the customers are having hard times, as we have seen in actually managing Kubernetes microservices and make sure that you can actually get the cloud native benefits. So Akamas is leverage AI, as we see that these kind of technologies are now mature to solve those kind of issues. By the way, we are seeing interesting other application of AI these days with ChatGPT, etc. So AI can also be used to actually optimize our Kubernetes environments, especially as we have seen most of the problems are basically related to configuration issues, not speaking about the code or not speaking about actually buying higher, better hardware, but actually let's make sure that the configuration are configured optimally to actually get the benefits. So basically, Akamas, one of the main benefits is that it allows you to actually define what is your own optimization goal. So basically, it's pretty flexible. So you can actually optimize for cost. So you can say, okay, I want to reduce the cost of my microservices, or you can use Akamas actually to improve the resiliency or to improve the performance of your microservices. So it's pretty flexible. And the other thing, as you can see on the bottom, basically, it's a full stack solution, meaning that we not only optimize Kubernetes settings like CPU limits, memory limits, as we have seen, but it is important to be able to optimize what runs within the container at the same time. Like we have seen most of the examples, basically those two layers are highly interconnected. So in order to realize the benefit of actually being able to deliver faster and more resilient application is crucial to being able to optimize the two layers at the same time. Basically, Akamas allows you to optimize application in two kinds of scenarios. So the first one on the left is what we call optimization studies. So basically, that's the ability of Akamas to optimize the application before they are launched in production, but when they actually work in testing environment. So actually, that means being able to leverage performance testing, performance engineering activities, and Akamas can actually automate the execution of performance tests and actually changes all the configuration for your stack based on AI, based on our reinforcement learning techniques in order to improve performance or reduce costs, as we have seen. The other most interesting scenarios, it's what we call live optimization. It's the one that we are going to see in a moment in our live demo, actually. So with live optimization, Akamas can actually optimize your application as they work in production. So Akamas in this scenario is actually able to monitor what is happening to the application. It's able to understand the traffic patterns. So it's able to actually understand when we have a peak or when we have idle periods, and basically adjust the configuration, recommend SRE teams or software engineers or performance engineers or DevOps people, actually what is the best configuration to apply to a Kubernetes microservice as it is running in production, so that you don't need actually performance testing in place. You don't need performance testing environments, performance testing scripts, etc. But you can get those kind of benefits by actually looking at the production and how the application actually work as they serve real life user traffic. So let me show actually an example. So actually one of the main topic about this webinar is showing a demo. So let me show you how Akamas AI, especially the live optimization, can optimize the cost. So again, that ties back to the most important driver that you also have told us in the first part. How do we optimize the cost of Kubernetes microservices? And as we have seen, it's very important to actually optimize Kubernetes and the runtimes and what runs within Kubernetes to really actually solve the challenges that we have seen before. So Java is one of the most common, actually the most common languages based on also industry reports about that runs on Kubernetes. So let's see how we can actually reduce the cost of a Java-based microservice running in production. So let me switch to our demo environment. All right, hope you see my screen. All right, so actually what you can see here is basically Akamas UI. So I have several running optimization here for different applications. So let me, as you can see, basically we have application that we have optimization that relates to different microservices in this environment. So we have optimization related to Kubernetes and Java. We have optimization related to Kubernetes and Node.js or Golang or .NET. Each one may have a different goal, as we have said before. So cost reduction, response time. Let's focus on this optimization, which has concluded, but it's very interesting because it ties back with all of the challenges that we have seen before. So first of all, let me show you how do we start with optimizing Akamas. So the first step is actually how within Akamas we describe your application. So that is the system, what we call the system. And you can see basically that's a pretty simple Java microservice. You can see we have Kubernetes pod, we have the Kubernetes container, the JVM, and we also have the web application. So if I click on the web application, basically we can see actually what are the most common metrics related to end-to-end application performance. So we have basically the throughput, error rate, the response time. Those kind of metrics, as we are going to see, are actually what we monitor from what we get from observability tools. So we import those metrics related to the performance of your services. If we move to the Kubernetes container, of course, we have metrics related to the container like CPU limit, request, throttle time, usual container performance metric. But most importantly, we have the parameters. Parameters are what actually are the knobs that actually Akamas AI will tune. So pretty simple ones related to Kubernetes, and most important ones are related to CPU limit, request, memory limit, and request, which actually again are related to the challenges that we have seen before. Those are the actual parameters. JVM, again, that's a Java application. What is important is, of course, being able to monitor all those metrics, but most importantly, the parameters. So again, what we can tune for a JVM, that ties back to what we were saying before. For example, that's a JDK 11. So within Akamas, we already have defined all the key parameters. So for example, garbage collection type, we can see all the garbage collection that we can specify for a JDK 11. We can see the actual string that you need to use. So no need to specify for you all those kind of options. We have already done the work ourselves, and that's actually include the most important parameters that you need to optimize on a JVM. Again, that's a JVM example, but basically that translates to all the other technologies like we have seen before. So let's go back to our study. So when we actually want to optimize a microservice with Akamas, what is very different with respect to other solutions is the ability to define the goal, as we have seen before. So basically with Akamas, we can say, okay, I want to minimize the cost. So the cost it's actually a metric. Again, that metric may come from, for example, the cloud bill, may come from basically the observability tools. What is important is that that's a metric that we come from actually any data source that you may have. We can say, actually, let's minimize this metric. So let's find configurations that actually minimize the cost. So that's one key part. Again, other studies you may create other optimization goals like let's minimize the response time, let's maximize the throughput, whatever you want. What is also key is the ability to actually express what we define, what we call constraint. So actually, I want to minimize the cost, but I don't want to impact application performance. Like we have seen before, it's very easy to reduce, for example, the memory and start suffering and slowing down the application. Akamas will take care of that because we are able to specify constraints, which kind of are mimic the SLOs if you apply this kind of concept in your operation. Basically, what we can say is that my response time, P90, for example, should be lower than 240 milliseconds. I don't want to have error rate higher than 2%. So that's kind of the different approach with AI. So we state the goal, we state our constraint, and then as you are going to see, AI will start recommending configuration that matches our goal. So completely different approach with respect to manual tuning, as you can see. The other important point is that it's full stack, like we say. So the ability to optimize both the container level and the JVM, so the runtime. Again, that's the JVM. We are going to see other example with Node.js or Golang, for example. So, for example, on the container CPU memory limit, pretty straightforward. But we are also optimizing the JVM. So max heap size, which ties back to the problem. So being able to size the heap in order to avoid out of memory, as you may recall, but also garbage collection that kind of has an impact on CPU throttling, like we have seen it before. So also we can specify a relationship among the parameters. So that is very key, for example, to avoid out of memory. So we say that we need to keep a buffer between the heap and the memory limit, as you may recall. So we can specify those kind of links, those kind of relationship among the different layers. So that is very important. So in this case, we are leaving a buffer of 1 gig between the max heap and the memory limit. So that's what actually make the application, the configuration actually robust with respect to out of memory errors. So that's the way basically you can configure an optimization. Let's see now the results. So that's a chart that shows basically over time what is happening to the main KPIs for this microservice. So basically what you can see here, let me add the throughput of this service. So that's a service that runs once in production. So basically what you can see here is basically the throughput in green. So usual kind of daily pattern that most of the application follow, right? So no big surprises here. So that's a metric that comes from Prometheus or from Dynamically, for example. Then you can see the response time, so P90 of the response time. So that is what actually Akamas will take care in order to not to slow down the application, as we are going to see. So that's the throughput, so pretty stable, pretty flexible. And now you can see the cost. So the cost is what we are actually monitoring from the cloud. And as you can see, the first configuration, so before actually starting to optimize, this microservice costs about $80 per month. That is the result of basically the initial configuration that we have, what we call the baseline. So in the baseline, this container will basically have 2,000 millicores, basically 2 CPUs, 3 gig of RAM, and a given configuration of the JVM. So that's the starting point, that's the starting cost. As you can see, basically, as time goes by, having issues with the webinar windows, apologize. Basically, as time goes by, the cost is going down. So why is that? Because actually Akamas is recommending different configuration of the different parameters. What is important to see is that after about 8 configuration, basically we already have reduced the cost pretty significantly. We are about 40% cost reduction on the cost of this microservice, which is actually a result of being able to downsize the container. So in this case, for example, Akamas suggested that 1 CPU, basically 100 millicores, and a given configuration of the memory limit, etc., would be enough to run this container. So that's the way it works. What is important to notice is also what is happening to application performance. Like we mentioned before, basically, we don't want to slow down the performance of our application. I've turned on the constraint, which we defined earlier. So our SLO in this case, or SLI, would be actually not to slow down more than 240 milliseconds. Look at what is happening here. Basically, Akamas found configuration that actually is bringing down the cost, but it's actually not slowing down the application. As you can see, the response time is pretty flat. What is interesting to see, for example, what happened in this moment, where actually we had a peak in the response time. There might be a peak in the load, or actually might be due to the effect of throttling, as we said before. But look at what is happening. At the next configuration, basically Akamas reacted to that. So Akamas understood that this configuration actually made the response time goes higher than our desired target, our desired threshold. And the next configuration basically take care of that. So it's increasing a little bit the CPU usage, the CPU limits in this case, actually to cope with the response time. So that's kind of the key difference with respect to other approaches that just look at infrastructure metrics like VPAs, which is actually often suggested as the way to right-size container. So VPA will not look at your performance and will simply crash the application, because actually it will simply recommend lower and lower limit until the application will start throttling and having out-of-memory errors, especially for JVM workloads. So that's one of the biggest advantage. The other thing that is very, very interesting is that let's look at what happens to the CPU. So let me put here the CPU limit. And the CPU used. So that ties back to actually the chart that we have shown before. So if you look at basically the baseline configuration, the CPU use was about one CPU and a half. We had a limit of 2 CPUs, as we have seen in the beginning. So look at what is doing Akamas. Akamas is basically recommending lower and lower CPU limits, and it also always, of course, taking into consideration what is happening to application performance. But look at here what is happening, something very interesting. So from configuration 7 to configuration 8, Akamas is able basically to bring down the CPU limit quite significantly as a result of basically the reduction of CPU usage. So as you can see across 2 different configurations, that is something very powerful. So not only Akamas lowered the CPU limit, but actually Akamas was able to reduce the CPU consumption. Why is that? That is the result of tuning the JVM. So what runs within the container. So configuration number 7, for example, had a particular garbage collector. G1 is actually one garbage collector designed to actually improve application performance, reduce the poses of the JVM, but that may have an impact on application, on CPU usage and throttling on containers. So on configuration number 8, basically Akamas changed it to parallel. Parallel may be much better in some situation. Of course, the parallel may use less threads, so maybe less prone to CPU throttling. Of course, it may actually slow down the application, but Akamas is monitoring that. So it's finding that parallel for this particular microservice is the best configuration, the best GC that you can achieve. And it's also adjusting CPU, the heap size and memory limit according to actually reduce further the cost of this application. So that is actually very, very important. Last piece that I wanted to show you is about the fact that if you look at, again, all those configurations over time, you may wonder, okay, are we applying configuration automatically, or is there any kind of approval system? Of course, we are changing configuration in production. People want to have control. So in this particular example, so Akamas is basically automatically applying. As soon as it comes up with a new recommendation, it's automatically applying basically to production. So as we can see also in the UI, basically we have this automatic mode. So again, Akamas will change automatically the configuration in production. But you can also specify the manual mode basically. So let me bring up this other optimization where I put the manual mode. So basically, from time to time, Akamas will recommend me to actually apply a configuration in production, and I have the chance here to basically review and approve the configuration. So in this case, it was generated 2 hours ago. Akamas is recommending me basically changes to the configuration parameters. I can actually select to let me use another example. I guess it should be better. Okay, so in this case, actually, you can see that Akamas present me the current values for the CPU limits and memory limit. That's an example for Go runtime, another very common language. So Akamas is actually recommending me, for example, a different setting for the Go GC, which is another variable that can impact application performance. It's presenting me differences about the delta. So it's actually helping me understand how big is this change. By the way, those are configurable. You can ask Akamas to be very gradual when recommendations are made, and I get a chance to approve. I get a chance to approve this recommendation. So again, I have a kind of recap of the changes that Akamas is suggesting, and I can select to approve this configuration for this to be applied in production. So I guess that's conclude the demo. So that's what I wanted to share with you. Let's go back to the slides. So I guess now we have the Q&A session. So very pleased to have a look at the question.
Great presentation. We actually have a question from Shir. I hope I'm pronouncing the name right. Which is, I think it's about the first fact that you showed about reducing memory limits. And the question is, why would reducing memory limits lower costs? Limits are for reliability, and containers will be scheduled by requests. So costs should be calculated by requests. So what's your, please take it.
Yeah. That relates to the fact that most of the people actually are running with requests equal to the memory limits. So actually, it's actually one of the best practices to run reliable containers in production. So actually, when we lower memory request and memory limit, actually we can translate to lower costs on the cloud. Or other times when actually you don't memory requests are lower than memory limit, still limits are actually in a way indirectly impacting the cost, because actually you can over provision your cluster with limits much higher than the actual request, of course, because Kubernetes, of course, is scheduling based on request. But actually, if your cluster is too highly overcommitted, so say that you have your limits like 400%, that is actually impacting the stability of the cluster. So we see people that kind of either are running with memory request and limits basically equal to be on the safe side, or either they are actually still kind of considering best practices like, let's put a threshold on the amount of overcommitment, and if we of course reach this kind of threshold, that translates to the need to buy bigger hardware. So that's the way where we see it.
Okay, and then there's another question, if you want to take it from Ben, about Akamas integrations. I would assume, with telemetry tools and the rest of the tool set, the performance engineering tool set.
Yeah, sure. So let me go back basically to the Akamas platform picture. Basically, depending on, of course, we have different integration with respect to pre-prod environments or prod environments. So for pre-prod environments, basically load testing integration is important. So we integrate with Load Runner, we integrate with JMeter, we integrate with Neoload, for example. So of course, we need to integrate with load testing tools. Those are very common ones, but also platform is very flexible. We integrate a lot of telemetry tools, of course, that is common also for production. So tools like, of course, Prometheus, but also Dynatrace, Datadog, and others. So the platform is pretty open. So we didn't want to reinvent the wheel. So not having agents. So Akamas doesn't require Akamas agents to be able to operate and bring those kind of benefits that we have seen. What is important in production is the ability to be able to integrate with CI/CD pipelines, for example. So the way that you have seen, when you approve when Akamas comes up with a new recommendation and you get a chance to approve it, basically what is happening? So what is happening is that Akamas could either actually apply the recommendation by talking directly with the Kubernetes APIs. That is one option. But most of the time, people that are actually using an approach like more GitOps oriented or more infrastructure as code oriented, they basically want Akamas to not change the cluster, not change the state of your application, but simply actually update the configuration. So basically what we can do in this case is basically open a merge request, for example, to our GitLab repo, and then a DevOps person might actually have the chance to review the change and approve the change and merge the changes. That has the advantage of course, integrating with your DevOps processes and not reinventing the wheel. There's no need for us to actually have the grants to change stuff in production, but simply let's do the work that you most likely already have done when designing your pipelines. That's the idea.
Thank you, Stefano. I think we ran out of time. We had some questions beforehand that were submitted to us before this event. Is there anything in particular that stood out that you would like to answer, Stefano?
Yeah, I think we have some of those. We should have some of those here, right? So how does Akamas apply the configuration is actually a common question we kind of answered before. So basically, we can either apply that or integrate with DevOps tools that actually take care of changing the configuration, basically manifest, and then taking care of the actual rollout in production. That's kind of the best practice that we see and that customer prefer. The other one is related to the best practice recommended for GC setup and how to free and release as faster allocated memory. So I guess this question has to do with the fact that traditionally JVMs are actually pretty greedy in terms of memory allocation. So they kind of allocate and use all the memory that you assign to them. Of course, that's kind of the problem when you want to auto-scale, for example, Java workloads. So what we are seeing here is that, of course, there's kind of progress in the JVM, in the OpenJDK project, to being able to actually make the JVM more kind of dynamic. So Parallel GC, for example, is already a dynamic collector. So not the newest one, but it has built-in capabilities actually to use and release the memory and being adapted the amount of memory used based on the workload. But also G1, which is kind of the newer one, is kind of more, is kind of way less greedy in terms of using the memory. So you will find that G1 will more closely follow the pattern of usage, and that is more kind of better suited for trying to auto-scale JVM workloads. Of course, you always have those kind of trade-off like CPU usage, performance, and reliability that we are talking about. So the recommendation here is always to try to do experiments, see what is the best GC for your specific microservices. So the other question I guess we kind of answered about, so what could be more recent tools. We have shown our approach.
Stefano, the tool is Akamas, right?
Yeah, that's hopefully that you will find it Akamas interesting. So the way that we can actually dramatically change the way that you can solve those kind of problems. So you can let the tool work and let AI comes up with better recommendation by analyzing all those microservices, all those performance signals, which is much better suited than the human brain for sure. But you still get, of course, this kind of control, the ability to actually to see the recommendation, apply them, etc. So that's, I guess that should be it.
Yes. So I think we're approaching the end of our webinar. Just maybe Stefano, a couple of notes, or where can people when do people can find you, or more information about Akamas? And just a minute to say we have plenty of resources on our website, so you can visit our resources library online at akamas.io/resources. We also have a Kubernetes specific content on the website, very easy to find. /Kubernetes is the link. And of course, we also have a free trial on the website. So if you want to try it for yourself, then I invite you to submit your free trial request on our website. And of course, if you want to meet Stefano in person, where can you do that? Not only him, but the rest of the Akamas team. The next opportunity is actually behind the corner. It's in February, on February 13, at Dynatrace Perform 2023 in Las Vegas in Nevada. So with that, I want to thank Stefano very much for this very interesting and super relevant content, given how common Kubernetes is becoming in so many organizations. Thank you very much, and we'll see you next.
Thank you everybody, and would love to continue the conversation. You can reach out to me on LinkedIn. So thanks again for your time today. Bye-bye.
Bye-bye.